I was looking at my phone this morning, scrolling through this feed of news stories that seem suspiciously tailored to exactly what I was anxious about yesterday, and I caught myself doing that thing we all do. I muttered, "The algorithm is out to get me today."
Yeah.
It's become this universal shorthand. It's the invisible hand, the ghost in the machine, the thing we blame um, for social media addiction or these weirdly specific ads. But as I was prepping for this, I realized I was using the word algorithm as a synonym for magic or maybe conspiracy.
That is the standard operating procedure for the 21st century. It
Yeah.
really is. We've elevated the algorithm singular with a capital A into this sort of digital deity. It sees all, it knows all, and it controls our attention.
Right.
But if you strip away all that Silicon Valley mysticism, that word has a very concrete, very rigid definition. And frankly, the reality of what an algorithm is, and I mean the mathematical reality, is far more interesting than the boogeyman version we talk about.
That's exactly why I wanted to do this deep dive. I want to dismantle that mysticism. We are going to trace this concept from its absolute origins, which surprisingly involve writing in mud, not coding in Python, all the way to the bleeding edge of quantum mechanics.
It's a huge journey.
It is, but I don't want to just stay in the history books. I want to understand the mechanics.
Yeah.
Because my understanding is that an algorithm isn't just code. It's a specific kind of logic.
Precisely. If you take nothing else away from this conversation today, it should be this. An algorithm is not inherently digital. It doesn't require a microchip. You can run an algorithm with a pen and paper.
Or a pile of rocks.
You can run one with a pile of rocks. At its core, an algorithm is a tool for solving a problem. But it's a very, very specific type of tool. It's not just a guideline. It's a wigger.
So let's start there. If I'm a computer scientist or a mathematician and I say I have an algorithm for this, what am I actually promising you? Because I feel like I use the word loosely to mean a method, but you're saying there's a stricter criteria.
Much stricter. So in a formal context, an algorithm is a finite sequence of well-defined, computer-implementable instructions, typically to solve a class of problems or to perform a computation.
Okay, that's a mouthful. Let's unpack that.
Let's do it. There are a few key words in there that carry all the weight. The big ones are finite and well-defined.
Finite seems obvious. It has to end. You can't have a recipe that just says stir forever.
You would think it's obvious, but in computation, it's a profound constraint. It's not just that it should end, it must end. An algorithm has to proceed through a series of well-defined successive states and eventually terminate with an output.
So an infinite loop.
An infinite loop is the classic example of what is not an algorithm. If you write a set of instructions that get stuck, where step 10 sends you back to step 5, and step 5 sends you back to step 10 forever, that is technically not an algorithm. It's a procedure that fails to halt.
It's a broken promise.
It's a broken promise. Exactly. An algorithm is a contract. You give me an input, any valid input for that class of problem, and I promise I will perform these specific steps and I will deliver an output. It is deterministic.
Deterministic, meaning what exactly?
Meaning if we both follow the algorithm for, say, long division with the same two numbers, we absolutely must get the same result every time. If we don't, one of us didn't follow the algorithm correctly. There's no room for interpretation.
Okay, so that brings up a tension I found in the research. We have this rigorous definition deterministic, finite, correct results, but then we look at the algorithms running Netflix or TikTok. Those don't feel deterministic at all.
Not in the slightest.
If I open my feed today and then I refresh it a second later, I get something different. And half the time, the recommendation is garbage. So is that actually an algorithm in the strict sense?
This is the crucial distinction that gets lost in the pop culture conversation. It's probably the biggest misconception out there. What we colloquially call the algorithm on social media is often a complex stack of systems, but the core decision-making part is largely based on heuristics, not just pure algorithms.
Okay, differentiate those for me. Algorithm versus heuristic.
An algorithm, in the pure mathematical sense, finds the correct answer. If I ask you to sort a list of 5,000 names alphabetically, there's only one correct order. A true sorting algorithm like merge sort or quick sort will find that exact verifiable order every single time. It optimizes for correctness.
Okay, that makes sense. One right answer.
Right. But now let's ask a different kind of question. If I ask a system, what is the perfect cat video to show this listener right now to maximize their happiness? Well, what's the correct answer to that?
There isn't one. It's completely subjective.
Exactly.
Yeah.
There's no scientifically verifiable correct answer. It's subjective. It's a moving target. And this is where we use a heuristic. A heuristic is a problem-solving approach that is practical. It's a shortcut, a rule of thumb.
So it's not trying to find the perfect answer because that's impossible.
It's not. And even if it were possible, it would be too slow. A heuristic doesn't guarantee the optimal or perfect solution. Instead, it provides a satisfactory solution in a reasonable amount of time. It trades precision for speed.
So it's a guess, a highly educated, statistically probable guess, but still a guess.
It's an estimation. I mean, think about it. If Netflix tried to calculate the mathematically perfect show for you by analyzing every frame of every movie ever made against a model of every neuron in your brain, the heat death of the universe would happen before the video loaded.
Right. That's not a great user experience.
Not at all. So instead, it uses a heuristic. A simple one might be, this person just watched 3 action movies starring Dwayne Johnson. They'll probably like another one. It's a shortcut that usually works.
That reframes the frustration people feel then. When the algorithm serves you something totally bizarre, it's not that the machine has some deep insight into your soul and is judging you.
No.
It's that the heuristic took a shortcut that didn't land. The rule of thumb failed.
Precisely. It's a rule of thumb encoded into math. And this concept of rules brings us to some really useful everyday analogies. We often hear that a recipe is an algorithm. And that's true, but only if the recipe is rigorous enough.
What do you mean?
Well, a step that says add salt to taste is not algorithmic. It requires human judgment. It's not well-defined. But a step that says add precisely 5 grams of sodium chloride, that is algorithmic.
Okay. It removes the ambiguity.
Completely.
Yeah.
Or think about a bureaucracy. I was thinking about this the other day. The DMV is a massive flesh and blood algorithm.
That's a truly terrifying image.
It is, but think about the structure. Input. Right. You walk in with a specific form, process, go to window 1, then there's a conditional statement. If the form is stamped, then proceed to window 2. If it is not stamped, go to the back of the line.
The dreaded else condition.
The else condition. And it continues like that, step by step, until you get the output, a driver's license or the rejection notice. The clerk in the window isn't supposed to use their own judgment or creativity. They are a processor executing a line of code.
So if the clerk starts making exceptions, oh, you seem like a nice person, I'll let that missing signature slide, they're essentially introducing bugs into the system.
Or features, depending on if the exception benefits you.
Yeah.
But yes, exactly. The whole system relies on the rigidity of the steps. And this need for rigid, repeatable steps is ancient. It predates computers by thousands of years. We tend to think this all started with Alan Turing or, Bill Gates. But the history of the algorithm is really the history of civilization trying to organize itself.
Let's go back to that origin, because the word itself, algorithm, it feels very foreign. It has that al prefix, like algebra.
Which is a dead giveaway of its Arabic origins. The etymology is actually a fascinating story of a game of telephone played across centuries and languages. We need to go back to the 9th century, to the House of Wisdom in Baghdad.
The intellectual center of the world at the time.
Absolutely. This was the hub of science, math, and philosophy. And there was a Persian scholar there named Muḥammad ibn Mūsā al-Khwarizmi.
Al-Khwarizmi. And if you say that fast enough...
Well, it takes a few centuries of mangling to get there. Al-Khwarizmi was a polymath, a true genius. He wrote a groundbreaking book around 825 AD. In Arabic, the title was something like Kitab al-Asab al-Hindi, which translates to the Book of Indian Computation.
Indian computation?
Yes. He was essentially introducing and synthesizing the Hindu-Arabic numeral system, our numbers 0, 1, 2, 3, and so on to the Islamic world. And from there, it was eventually transmitted to Europe.
So before this, Europe is stuck using Roman numerals.
Yes. And just try doing long division with Roman numerals. It's an absolute nightmare. How do you divide CXA3 by 9x? Doesn't work well at all. Al-Khwarizmi's book laid out the step-by-step procedures for how to add, subtract, multiply, and divide using the decimal system and place values. It was revolutionary.
So he wrote the algorithm for doing arithmetic?
He wrote the book on it. When his works were translated into Latin in the 12th century, the translators were faced with his name, Al-Khwarizmi. They didn't know what to do with it, so they just Latinized it. It became algorismus.
So algorithm originally just meant doing math with decimals, the new way.
Exactly. Algorism was the name of the newfangled method of calculation. It was contrasted with the old way, using an abacus. But then, fast forward a few hundred years to the 15th century, European scholars are rediscovering classical Greek texts.
Right.
They look at this word algorism, and they mistakenly confuse it with the Greek word arithmos, which means number. It's the root of our word arithmetic.
They thought it had a Greek root that it didn't actually have.
Right. They thought it was a spelling error. So they corrected it. They changed the as in algorismus to a the to make it look more Greek.
Ah,
And so algorism became algorithm. It was essentially a typo that stuck.
I love that. The very word for a precise, rigid set of instructions comes from a sloppy translation error.
The irony is pretty thick, isn't it? But while the name comes from the 9th century, the actual practice is much, much older. If we define an algorithm as a step-by-step procedure to solve a problem, we can find them written in cuneiform on clay tablets in ancient Mesopotamia, dating back to around 2500 BC.
This is the Sumerian stuff.
Yes. Archaeologists unearthed these tablets near Baghdad, and they are, for all intents and purposes, textbooks. They lay out procedures for division and for calculating compound interest for loans.
So even back then, algorithms were about money.
Some things never change. But they didn't have algebraic symbols like X or Y. They wrote it out in prose, like a recipe. Take the number, find its reciprocal, multiply by the dividend. It's a script for a human computer to follow.
And the Babylonians took this further with astronomy, right? I read they were incredible record keepers.
The Babylonians were obsessed with predicting the future, both for religious and agricultural reasons. Where will the planet Jupiter be next month? When is the next solar eclipse? You can't just eyeball that. You need a rigorous calculation.
And they developed algorithms for that.
They did. They developed incredibly sophisticated algorithms to track and predict planetary motion, all using a base 60 number system.
Which is why we still have 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in a circle. We are running Babylonian legacy code.
We absolutely are. It's baked into our daily lives. And the Egyptians were doing the same. The Rhine Mathematical Papyrus, which dates to around 1550 BC, is basically a textbook of algorithms for architects and scribes. It has step-by-step guides on how to calculate the slope of a pyramid or how to fairly divide loaves of bread among workers.
Practical problems.
Very practical. It's all about process. And that brings us to the Greeks, who really formalized the idea of mathematical proof and logic. There's one ancient algorithm I bet you remember learning in school. It's probably the only one that gets taught by name in a non-computer science class. The sieve of Eratosthenes.
The sieve, yes,
yeah.
for finding prime numbers.
Exactly. And it's such a beautiful, elegant, tactile algorithm. It's a perfect example of how an algorithm differs from just randomly looking for something.
Walk us through it, because the process is the whole point.
Okay, so imagine you have a big scroll, and you list out all the numbers from 1 to, say, 100. You want to find all the prime numbers in that list. The brute force way would be to look at each number individually. Is 91 prime? Let me try dividing it by 2, then by 3, by 4, by 5. That's incredibly slow and error-prone.
Right.
Eratosthenes, a Greek mathematician around 200 BC, came up with a much smarter process.
An algorithm.
Start with the first prime, 2. Circle it. Now go through your entire list and cross out every multiple of 2. So 4, 6, 8, 10, all the way to 100. They're all gone. You've eliminated half the numbers in one pass.
Pretty much. Step 2, find the very next number on your list that isn't crossed out. That number is 3. Circle it. It must be prime. Now go through the list and cross out every multiple of 3. So 6 is already gone, but 9, 15, 21, you cross them out.
And you just keep repeating that same instruction. Find the next available number, circle it, then eliminate all its multiples.
You just keep turning the crank. The next number is 5. Circle it, cross out its multiples, then 7. And you keep going. When you finish, every single number that is left, the ones that haven't been crossed out, must be prime. You don't have to check them individually. The process guarantees the result.
That's the key. It's the elimination of guesswork and redundant work.
It's the triumph of process over brute force. And speaking of eliminating guesswork, we have to mention another giant from that Islamic golden age. We talked about Al-Khwarizmi, but we have to talk about Al-Kindi. He was working around the same time, also in Baghdad.
This is the code breaker.
The father of cryptanalysis. Before Al-Kindi, if you intercepted a secret message where every letter was substituted for another, a simple cipher, you just had to guess. It was pure trial and error.
Brute force again.
Right. But Al-Kindi, who was also a musician and an optician and a philosopher, had a key insight. He noticed a pattern in language itself. He realized that in any given language, some letters appear far more often than others. In English, for instance, E's is everywhere. Z is very rare.
Frequency analysis.
He invented it. He turned that observation into a rule, an algorithm for breaking codes. Step 1. Get a long, unencrypted text in the target language and count the frequency of every letter. E appears about 12% of the time, T about 9%, and so on. Make a table.
Right.
Step 2. Take the secret encrypted message and count the frequency of every symbol in it. Step 3. Assume the most common symbol in the secret message corresponds to the most common letter in the language, so you swap it with E. Then swap the second most common symbol with T. You keep doing that.
And the message starts to reveal itself.
It starts to become readable. He turned code breaking from a mystical art into a statistical science, a repeatable process.
This brings us to a really interesting pivot point in the story. All of these examples, Sumerian division, the Greek sieve, Arab code breaking, they were all algorithms designed to be run by humans. The computer was a person with a stylus or a quill pen.
Yes, the wetware.
Exactly. But at some point, we decided we wanted to outsource the labor. We wanted to mechanize the process of thinking.
The mechanization of the algorithm. This is the industrial revolution of thought. And oddly enough, the conceptual bridge isn't a calculator, it's the clock.
The clock? How so?
Think about the verge escapement mechanism in a weight-driven mechanical clock from the Middle Ages. That tick-tock sound. That is the sound of a machine controlling the release of energy in discrete, quantized packets. It is a machine that follows a rigid, unthinking rule set to divide the continuous flow of time into identical units.
Okay, I see that. It's automation.
It's automation. And it inspired the idea of automata, these intricate machines and clockwork figures that could move by themselves according to a preset program. This planted the seed of an idea. If we can make a machine follow rules to move, can we make one follow rules to think?
And this leads us to the 19th century, and the two people who I think are the most fascinating what-if story in the history of technology, Charles Babbage and Ada Lovelace.
The tragedy of Babbage and Lovelace is that they were living in 1840, but they were thinking in 1940. They were a century ahead of their time.
So tell us about Babbage.
Charles Babbage was a brilliant but famously grumpy English mathematician. He was frustrated by the errors he found in hand-calculated mathematical tables, like logarithm tables. These were full of mistakes made by the human computers who compiled them, so he set out to build a machine to do it perfectly. His first design was the difference engine.
The one we really care about is the second one, the analytical engine.
Yes. The analytical engine was a massive leap forward. It wasn't just a special-purpose calculator like the difference engine. Because calculators already existed in some form, Pascal had built one in the 1600s.
Right. So what made the analytical engine different?
It was designed to be a general-purpose computer. It had all the fundamental components of a modern computer, just built out of brass gears and steam power. It had a store, what we would call memory, or RAM. It had a mill, what we would call the central processing unit, or CPU.
And it took its instructions from punch cards.
Yes. He borrowed the idea from the Jacquard loom, which used punch cards to control the patterns in woven fabrics. A hole in the card meant one thing, no hole meant another. Babbage realized he could use this to feed not just data, but instructions into his machine.
But he never actually built it.
He never fully built it. He was a perfectionist. He kept changing the design. He ran out of funding from the British government, and he alienated most of his machinists. It was this incredible, sprawling brass and scheme monster that existed almost entirely on paper.
And this is where Ada Lovelace comes in.
This is where Ada Lovelace, the daughter of the poet Lord Byron, enters the story. She was a gifted mathematician, which was rare for a woman of her era. She met Babbage, saw his plans, and understood them perhaps better than he did. She saw something he had missed.
What was that?
Babbage saw his machine as a supercalculator, a number cruncher. Lovelace saw its potential as a symbol manipulator. She realized that the numbers in the machine didn't have to just represent quantities.
This is that famous quote I have in the notes. She wrote that the engine might compose elaborate and scientific pieces of music of any degree of complexity or extent.
That is the conceptual moment the modern computer is born. That's the leap. She understood that a number in a gear could represent a musical note. It could represent a letter of the alphabet, a logical state, a pixel. If you can write an algorithm to manipulate numbers, you can write an algorithm to manipulate any kind of symbol. You can compute reality.
And to prove it, she wrote the first program for this theoretical machine.
She did. She translated a paper about the analytical engine, and in her own notes on the translation, which were 3 times longer than the original paper, she included a detailed, step-by-step algorithm to calculate a complex sequence of numbers called the Bernoulli numbers.
And that's considered the first piece of computer software.
It is widely cited as the first algorithm specifically designed to be executed by a machine, written a full century before the first electronic general-purpose computer, ENIAC, was built. She is rightly considered the world's first programmer.
But since the machine wasn't built, The theory kind of went dormant for a while. It was this fascinating dead end until the 20th century. And then we get Alan Turing.
Turing, the man who formalized everything. In 1936, he published a paper that is arguably the most important single document in the history of computer science, on computable numbers.
And he wasn't trying to build a computer. He was trying to solve a logic puzzle.
He was. It was a famous problem posed by the mathematician David Hilbert called the Entscheidungsproblem, the decision problem. The question was, essentially, is there an algorithm that can take any logical statement and determine, yes or no, whether that statement is universally valid?
Sort of a truth machine.
A universal truth machine. To answer this question, Turing had to first define what an algorithm or a method of computation actually was. And to do that, he invented a thought experiment, the Turing machine.
Now again, this isn't a physical machine you can go out and buy at Best Buy.
No, it's a mathematical model of computation. It's the simplest possible computer you can imagine. Imagine an infinitely long tape of paper divided into squares, like a roll of toilet paper.
Nice.
And there's a little box, the head, that sits over one square at a time. This head can do only three things. It can read the symbol on the square, it can write a new symbol on the square, and it can move one square to the left or one square to the right.
That's it. Read, write, move.
That's it. And it has a little book of rules, a state table, that tells it what to do. For example, a rule might say, if you are in state 4 and you read a 1, write a 1, move to the right, and change to state 6.
It sounds incredibly simple, almost too simple.
That's the genius of it, because Turing proved that this incredibly simple mechanism can perform any computation that is possible to perform. If an algorithm exists to solve a problem, a Turing machine can run it.
This is the universal Turing machine.
Exactly. Your iPhone, a supercomputer at NASA, they're just very, very fast, very small, very fancy Turing machines. They don't do anything fundamentally different from read, write, and move based on a set of rules. This is the theoretical basis of all modern computing.
But Turing also proved something devastating with this model.
He did. By defining what was computable, he could also prove that there are some problems that are uncomputable, problems for which no algorithm can ever exist.
This is the halting problem, right?
The famous halting problem. In simple terms, the question is this. Can you write a program, let's call it program H, that can analyze any other program and its input and tell you with 100% certainty if that other program will eventually finish, that is, halt, or if it will get stuck in an infinite loop and run forever?
And the answer is?
The answer is a resounding no. It is logically impossible. He proved it with a beautiful contradiction. You can't write a general-purpose algorithm that can perfectly predict the behavior of all other algorithms. This means there are hard, fundamental limits to what computation can ever achieve. We can't solve everything.
That is a humbling thought. We built these machines to be these perfect logical engines, and right at their theoretical foundation, there's a giant sign that says, "Here be dragons," or "Some problems are unsolvable."
Exactly. But for the problems we can solve, the next logical question is, well, how efficiently can we solve them? Because as we moved from Babbage's gears to vacuum tubes to silicon chips, we quickly realized that not all algorithms are created equal. Some are incredibly fast, some are agonizingly unusably slow.
And this is where we get into algorithmic analysis. This is the stuff that makes first-year computer science students sweat.
The dreaded big O notation.
Right. Let's try to demystify this. The key idea, as I understand it, is that we don't measure an algorithm's speed in seconds, right? Because a supercomputer from 2024 is obviously going to be faster than a desktop from 1994.
Correct. Measuring in seconds is useless because hardware keeps getting faster. So instead, we measure an algorithm's efficiency in terms of its growth rate. How many steps or operations does the algorithm take relative to the size of the input? We use the letter N to represent the size of the input.
Okay, N. So if I'm sorting a deck of playing cards, N is 52. If I'm sorting the phone book for New York City, N is, what, 8 million?
Exactly. And big O notation describes how the number of operations grows as N gets bigger. Let's start with the best case scenario. This is called O1, or constant time.
Constant time.
This means that no matter how big N is, the task always takes the same amount of time. It takes just one step. An example would be, give me the first name on a list. Whether that list has 10 names or 10 billion names, grabbing the very first one is a single operation.
That's the dream. Instant access, regardless of scale.
It is. The next level up is ON, or linear time. This is the most intuitive one. This is our brute force search. If I ask you, is the name Waldo in this unorganized pile of 100 papers? You have to look at every single paper one by one.
You might get lucky and find them on the first try.
You might. That's the best case. But we care about the worst case. In the worst case, Waldo is on the very last paper, or not there at all. So if you have 100 papers, N100 could take you 100 steps. If you have 1,000,000 papers, it could take 1,000,000 steps. The work grows in a straight line, equally with the data.
It's manageable for small tasks, but it doesn't scale well if you have truly big data.
Not at all. And this is why the next level up is where the real magic of computer science happens. This is O log n, or logarithmic time.
This is the phone book analogy.
The classic phone book analogy. It perfectly illustrates the power of an algorithm called binary search. So imagine the phone book again with its millions of names. But this time, critically, it's sorted alphabetically. You're looking for Smith. You don't start at A and read every name. That would be O-N.
Well, you open it roughly to the middle.
You open it to the middle. You see names starting with M. You know, Smith comes after M. So you can take the entire first half of the book from A to M and throw it away.
You just deleted half the problem in a single step.
In one step. Then you take the remaining half from M to Z and you cut that in half. You land on R, still not there. Smith is after R. So you throw away the M to R section. You keep splitting the problem in half again and again.
So how much faster is that, really?
It's astronomically faster. Let's use that phone book of, say, 1,000,000 names. A linear search, O, in the worst case, takes 1,000,000 steps. A binary search, O log n, takes about 20 steps.
Wait, only 20? From 1,000,000 down to 20?
That's the power of logarithms. 2 to the power of 20 is roughly 1,000,000. You only need to cut the deck 20 times to find one specific card in a deck of 1,000,000. This is what makes searching massive databases possible. This is the power of a good algorithm. It turns an impossible task into a trivial one.
But then there's the dark side, the bad algorithms, the ones that cause systems to grind to a halt.
Oh, yes. The ones to be avoided at all costs.
Yes.
The next step up is ON, or quadratic time. This is what often happens when you have a nested loop, when you have to compare every single item in a list to every other single item in that list.
Can you give me an example?
Sure. Imagine you have a list of 100 people in a room, and you want to see if any 2 of them share a birthday. The simplest algorithm is to ask the first person their birthday, then compare it to the other 99 people. Then you go to the second person and compare their birthday to the other 98 people. You see, for n people, you're doing roughly n-squared comparisons. So if you have 10 people, it takes about 100 comparisons. If you have 100 people, it takes 10,000. If you have 1,000 people, it takes 1,000,000 steps. The complexity explodes. This is why a startup's new social media app works perfectly fine with 50 beta testers and then completely crashes the moment they get 5,000 users. Their algorithm was probably OM.
And it gets even worse than that, doesn't it?
It gets much, much worse. The truly terrifying one is O to N, or exponential time. This is the heat death of the universe algorithm. With exponential time, if you add just one more element to the input, you double the amount of work.
Double it.
Double it. The traveling salesman problem we mentioned earlier is a classic example. Finding the absolute shortest route to visit in cities requires checking a number of paths that grows exponentially. If you can solve it for 20 cities, adding the 21st city makes it twice as hard. Adding the 22nd makes it 4 times as hard. Very quickly, the problem becomes unsolvable for even the fastest supercomputers.
So our modern security, like for banking and things, is basically relying on the inefficiency of these kinds of algorithms.
Exactly. Modern encryption is built on the fact that certain mathematical problems, like factoring a very large number into its 2 prime components, are believed to be in this exponential or near exponential class for classical computers. It's not that it's impossible, it's that the O2N algorithm would take so long to run that the sun will burn out before it finishes. We rely on problems being intractable.
We also need to touch on space complexity. We always focus on time, on speed, but computers have a finite amount of memory.
Right, and there's very often a direct trade-off between the two. We call it the space-time trade-off. You can frequently make an algorithm run faster by allowing it to use more memory.
How does that work?
Think of it like this. You're a travel agent, and you constantly need to know the driving distance between any 2 major cities in the country. Option A is to save space. Every time a client asks, you use a mat and a formula to calculate the distance on the fly. This takes time, CPU cycles, but uses very little memory. Option B is to save time. You spend a week calculating the distance between every possible pair of cities and write it all down in a giant lookup table, a huge book. Now, when a client asks, looking up the answer is instant, very fast time complexity, but you have to store and carry around this enormous book, which takes up a huge amount of space or memory.
And modern computers have so much cheap RAM that we usually lazy and choose option B.
We do. We are very wasteful with space today in many applications because memory is cheap. But back in the 1960s, programming for the Apollo missions, or even today in small embedded systems like the chip in your toaster, your car's engine, space complexity is absolutely critical. You have to be frugal.
So we have the metrics for judging them. Now I want to open what you called the bestiary. I want to walk through the different species of algorithms, the different paradigms, because they really do have different personalities.
They really do. They have different philosophies of problem solving.
Okay, let's start with the one we've touched on already, brute force, the try everything approach.
Brute force is the simplest, most obvious, and often dumbest way to solve a problem. It's about systematically trying every single possible option until you find the right one. The quintessential example is cracking a password. If you don't know the password, you try A, then B, then C, then A-S-E.
It's guaranteed to work eventually.
Guaranteed. But for any non-trivial password, eventually might be longer than the age of the universe. It's the baseline against which smarter algorithms are measured.
Okay, so a smarter approach might be divide and conquer.
Yes. Divide and conquer is a very powerful and elegant strategy. It's military strategy applied to math. You're faced with a huge, scary problem. The philosophy is, don't try to solve the huge problem. Break it down into smaller, identical subproblems. Solve those little subproblems, and then combine their solutions to solve the original big one.
This is the merge sort algorithm you mentioned for sorting lists.
Merge sort is the textbook example. You have a huge unsorted list of numbers. Don't try to sort it all at once, just split it in half. Now you have two smaller, easier problems. Split those halves. Keep splitting and splitting until all you have are tiny little lists with just one number in them.
And a list with only one number is, by definition, already sorted.
It is. The conquer part was easy. Now comes the combine part. You start merging those little one-item lists back together into two-item lists, but you merge them in sorted order. Then you merge the two-item lists into sorted four-item lists. You keep zippering them back together, and at the end, you have one big, perfectly sorted list. It's elegant, it's reliable, and it's much, much faster. A dumb sort like bubble sort.
So divide and conquer is about breaking a scary problem into a bunch of tiny, non-scary problems.
Precisely. Now, related to this is the concept of recursion versus iteration. These are two different ways to implement that repeat a process idea.
Okay.
Iteration is the one most people are familiar with. It means using loops, a for loop or a while loop. You're explicitly telling the computer, do this thing 10 times, or keep doing this thing until this condition is met. It's very direct. Recursion is a bit more mind-bending. A recursive algorithm is one that calls itself to solve a smaller version of the same problem.
It calls itself.
It calls itself. The classic example is the Tower of Hanoi puzzle. To move a stack of 5 disks, the recursive solution is move the top 4 disks to the spare peg, then move the bottom disk to the destination, then move the 4 disks on top of it. But how do you move 4 disks? Well, the algorithm calls itself. To move 4 disks, you first move 3 disks. It keeps breaking it down until it gets to the simple case of moving just 1 disk.
Sounds elegant, but also potentially dangerous. Like it could easily lead to an infinite loop.
It can if you're not careful. Every recursive algorithm needs a base case, a condition that tells it when to stop calling itself and just return an answer. Without that, you get a stack overflow, which is the recursive version of an infinite loop.
Let's move on to the greedy algorithms. You call these the impulsive ones.
The ones that lack long-term vision. A greedy algorithm makes the locally optimal choice at every single stage, hoping that a series of locally optimal choices will lead to a globally optimal solution.
The live-in-the-moment algorithm.
Exactly. Imagine you are navigating a maze where every path is lined with coins. A greedy algorithm stands at a junction. It looks left and sees a path with 1 coin. It looks right and sees a path with 5 coins. It immediately goes right. It doesn't care if the path on the right leads to a dead end or a monster 10 steps later. It wants the biggest payoff right now.
The marshmallow test of algorithms. It always eats the marshmallow.
Yes. It has no impulse control. The traveling salesman problem is another good example. The greedy approach says, from where I am now, what is the absolute closest city I haven't visited yet? Okay, I'll go there. And it repeats that from every city.
And does that actually work? Does it give you the shortest overall path?
It gives you a path, and it's very fast to calculate. But it usually isn't the shortest path. It might send you to a nearby city that is way out on a limb, forcing you to make a very long trip later on. It gets stuck in local optima.
So if you need the absolute best, perfect path, greedy fails, what do you use instead?
Well, for that kind of problem, you might use dynamic programming. This is like the smart, cautious older sibling of the greedy algorithm. Dynamic programming also breaks a problem down into subproblems, but it has a memory. It uses a technique called memoization.
Memoization, that's M-E-M-O, not memorization.
Right. Memoization. It literally means writing it down in a memo. Imagine you are calculating the Fibonacci sequence, where each number is the sum of the previous two. A naive, recursive algorithm to find the 50th number would be incredibly slow because it recalculates the same values over and over and over again.
Okay.
A dynamic programming algorithm says, wait a minute, I've already calculated the value for the 10th Fibonacci number. I wrote it down in my notebook. Instead of recalculating it, I'll just look it up. It caches the results of subproblems so it never has to do the same work twice.
And that's a huge speed up.
It turns many exponential problems into linear or polynomial ones. This is fundamental to how things like Google Maps can find the shortest route so quickly. It doesn't recalculate every road in the world every time you ask for directions. It uses known distances of smaller segments, solved subproblems, to stitch together a full route.
I want to touch on one more category that seems really counterintuitive to me. Randomized algorithms. Why on earth would we want a computer, our machine of pure logic, to do something random?
This is for when the problem is so monstrously big or complex that finding an exact answer is just too expensive or would take too long. Sometimes, a probably correct answer that you can get in a second is much more valuable than a guaranteed correct answer that takes a year. We generally have two flavors: Monte Carlo and Las Vegas.
Named after the gambling meccas, I assume.
They are, and the analogy is perfect. A Las Vegas algorithm is like a slot machine that is guaranteed to eventually pay out the jackpot. It always gives the correct deterministic answer, but you don't know how long it will take. You might get lucky and it finishes in a second, or you might be sitting there pulling the lever for an hour, but you can trust the result when you get it.
Okay, so always correct, but runtime is random. What about Monte Carlo?
A Monte Carlo algorithm is the opposite. It runs for a fixed, predictable amount of time, but the answer it gives has a small probability of being wrong. It's like playing a round of poker. You finish the hand in a few minutes, but you might have lost. It might say, the answer is 42, and I'm 99.999% sure about that.
Why would you ever accept a 99% answer? When is that good enough?
A great real-world example is testing for prime numbers for cryptography. We need to find huge prime numbers, numbers with hundreds of digits. Proving with 100% mathematical certainty that a number that big is prime is very, very slow. But there's a Monte Carlo algorithm called the Miller-Rabin primality test. It runs a few random checks on the number. If the number passes all the checks, the algorithm says, this number is almost certainly prime.
And almost certainly is good enough for our online security.
It is. The probability of it being wrong after, say, 100 rounds of testing is so astronomically low, less than your chance of being hit by a meteor, that for all practical purposes, it's considered true. It's an engineering trade-off. Engineering accepts tolerance. Pure math does not.
We've covered the mechanics, the types, the theory. I want to move to the real-world implications, specifically the legal side. If these algorithms are such valuable tools like industrial machines, can I own one? Can I get a patent on an algorithm?
This is a legal and philosophical minefield. The short answer, in the United States at least, is no, you cannot patent math. You cannot patent the Pythagorean theorem. You can't patent E-Maser. They are considered fundamental truths of the universe, abstract ideas, and they belong to everyone.
Software companies have thousands of patents. Amazon has a patent on one-click buying. That's an algorithm.
They do, and this is where the legal nuance comes in. The distinction the courts have tried to draw is between patenting the abstract idea and patenting a specific practical application of that idea. You can't patent the formula, but you might be able to patent the machine or process that uses the formula to do something tangible in the real world.
What's the key case there?
The landmark case is Diamond v. Dyer from 1981. It was about a process for curing synthetic rubber.
Rubber curing. Not exactly the glamorous side of Silicon Valley.
No, but it was a critical industrial process. The company had a computer running a well-known mathematical formula, the Arrhenius equation, to calculate the perfect curing time. The algorithm constantly raised the temperature inside the rubber mold and reran the calculation to determine the precise moment to open the press. The U.S. Patent Office rejected their patent, saying you're just patenting a mathematical equation.
But the Supreme Court disagreed.
They did. The Supreme Court overruled them. They said that because this algorithm was part of a larger process that was physically transforming rubber from an uncured state to a cured state, because it was interacting with the real world in a tangible way, the overall process was patentable.
So if my algorithm just sorts numbers on a computer screen, it's an abstract idea and hard to patent. But if my algorithm controls a robot arm that sorts physical apples into bins, I can patent the whole process.
That's a good way of looking at it. Generally, yes. But it is still a hugely debated area of law. There's a lot of controversy over software patents stifling innovation. If someone patents a fundamental way of compressing video, suddenly nobody else can stream movies without paying them a license fee. It's a constant tension between protecting inventors and allowing the free flow of ideas needed for progress.
And speaking of progress, we have to look at the horizon. Because there's a new kind of computer coming, which means there's a new kind of algorithm on its way. We are entering the era of quantum algorithms.
You're a quantum leap. It's a whole new paradigm.
We hear the buzzwords all the time: qubits, superposition, entanglement.
Yeah.
But from a purely algorithmic standpoint, what actually changes?
In a word, everything. All the classical algorithms we've discussed, from Euclid to Google, are built on the principles of a Turing machine. They operate on bits. A bit can be a 0 or it can be a 1. That's it. Quantum algorithms run on quantum computers, which use qubits. And a qubit, because of the principle of superposition, can be a 0, a 1, or it can be in a state that is partly 0 and partly 1 at the same time. This allows for a kind of massive parallelism that classical computers can only dream of.
So what does that mean for problem solving? For our big O notation?
It means that for certain specific types of problems, the complexity class can collapse. The most famous example, the one that keeps cryptographers up at night, is Shor's algorithm.
And what does that do?
Remember we said that factoring a huge number into its prime components is an exponentially hard problem for classical computers, that it would take millions of years. That's the foundation of most of our current encryption.
Right.
Shor's algorithm, if you could run it on a large, stable quantum computer, could factor those huge numbers in hours, maybe minutes. It breaks RSA encryption wide open.
So it basically breaks the internet as we know it.
It breaks a huge chunk of the security infrastructure of the internet, yes. It turns a classically intractable exponential problem into a manageable polynomial one. That is why organizations like NIST, the National Institute of Standards and Technology, are in a controlled panic, well, they call it proactive preparation. Just in 2024, they released the first official standards for post-quantum cryptography.
So they're already building new encryption algorithms that are designed to be hard, even for quantum computers to solve.
It's the next phase of the arms race, the code makers versus the code breakers. It's a race that started with Al-Kindi and frequency analysis in the 9th century, and it's continuing today with quantum physicists and cryptographers.
It really is just one continuous line, isn't it?
Yeah.
So let's try and wrap this all up. We've gone on an incredible journey. We went from Sumerian clay tablets to Al-Khwarizmi's name getting mangled, to Ada Lovelace dreaming of computer music, to Alan Turing's theoretical limits, and now to quantum encryption.
It's the history of human problem solving, really.
It is. And we learned that algorithm isn't magic. It's a rigorous recipe. We learned that efficiency isn't about seconds. It's about scaling, about avoiding those ON or O-time traps. We've met the greedy algorithms, the divide and conquer ones, the cautious dynamic programming ones.
It's a vast and fascinating ecosystem of thought.
But I want to leave our listeners with that provocative thought you mentioned when we were prepping for this. We spent this whole time talking about deterministic algorithms, machines, logic, rigid rules. But nature has its own algorithms, doesn't it?
Yes, and this is where the strict definition starts to blur and get really interesting. If you look at an ant colony foraging for food, there's no central leader, no single ant knows the map. But the colony as a whole runs a highly efficient search algorithm. It uses pheromone trails as a form of distributed memory to optimize the path to a food source. It is a distributed emergent biological algorithm.
And what about our own brains?
Our brain is a massive neural network. It doesn't run if-then code like a laptop. It learns, it recognizes patterns, it adjusts the weights and connections between its neurons based on experience. It is a constantly running adaptive learning algorithm.
So in a way, we are building these silicon-based algorithms that are, in many cases, just trying to mimic the biological algorithms that created them in the first place.
And we ourselves are the product of 4 billion years of the grandest algorithm of all. evolution by natural selection, a brute force, iterative process that optimizes for one thing, survival and reproduction.
So that leaves us with the final question for everyone to chew on. If a recipe is an algorithm, and a bureaucracy is an algorithm, and an ant colony is an algorithm, are you just running a very complex biological algorithm right now? Are we the programmers, or are we just the code?
That is a question that might not have a halting state. You could loop on that one for a good long while.
I think I will. This has been a fantastic deep dive. Thank you so much.
My pleasure. It was a lot of fun.
See you next time.